so sticky question. How do you separate molecules that are attracted to one another? We're going to talk a little bit about the post-lab here. Let's see if there's anything.
I haven't even done the pre-lab.
The pre-lab, I think you guys are going to be okay with. Maybe not, but as I mentioned before, the explanation to strengthen student understanding should help you out with the pre-lab questions. If you have issues with those, you can come talk to me if you're still not sure how to answer some of them. There's a lot of explanation here. All right. Now, most of our post-lab questions are going to focus in on why things happened the way that they did. Now, the issue is you might not have all of the data yet. We're going to get the data tomorrow when everyone comes in because some groups needed to let their stuff dry before they could actually even make their measurements. So we're going to compare RF values for all the different solvents very quickly at the beginning of class tomorrow, and that should give you the data that you need to confirm what we're talking about right here, okay? And I think as I was walking around and watching what was happening, I think big picture our ideas are going to be confirmed. I was still having trouble today seeing the blue on most of them. The red and the yellow, you could see the separation pretty well. I don't know if maybe we just needed bigger, longer papers. We needed to give it longer time. You couldn't see which solvents did you use? Acetone and ethanol. Okay. That doesn't surprise me a ton. You did see some movement though, right? Okay, yeah. So let's just kind of talk about the post-lab here. Whoops, did I go too far? Oh, here they are. Okay, so after your procedure, there's a section here, data collection and computation, and then an argumentation and documentation section. So how to fit that into the mold that we have built for ourselves here. What's after procedure? I'm going to have to look. So I want to make sure that we talk about the write-up here a little bit as well. Come on. All right, so what is this doing this? Oh, there we go. So we are to the probably what observations and measurements did I make. So then we've got what can I claim, what evidence do I have to support the claim, how do my ideas compare with others into the literature, and how have my ideas changed. The claim section, what we want to talk about there is probably something along the lines of what were the best solvents to use in this particular chromatography experiment, okay? And you'll be able to make that claim a little bit better after tomorrow, after we compare everybody's data. All right, you're going to be able to start to make that claim based on the post-lab questions we're going over right now. Okay, which I don't know. Making this video today, I'm sort of putting the cart before the horse a little bit, but I didn't want to make this video tomorrow because I wanted you guys to focus on studying for the test tomorrow, not this lab. So. Let's see. So as far as the claim, again, we would talk about which solvents did the best job, and then your evidence for that would be your RF data, okay, which you will have all of that data tomorrow after everyone calculates it, okay? How do my ideas and results compare with others into the literature? I will give you the literature values for the RF tomorrow. I don't care about you comparing it with others necessarily in the class itself. I want you to compare it to the data, okay? And then we'll see how close we got as far as the RF values that we calculate for the ones that we can calculate it for. And then in the how have my ideas changed section, just by default, because that's the last section, that's where I'll have you answer the post-lab questions, all right? So, and we'll call these data collection and computation questions, we'll call those the post-lab questions for this one. Okay, so that'll go in the how did my ideas change section, just because I don't really have a better place to put it for this lab. Yeah. So these post-lab questions will go into your section, how have my ideas changed. Okay. that make sense? So you have your heading, how have my ideas changed? That's where the post-lab questions will go. Okay? And here are the post-lab questions. Okay? So number one, this is going to be more of an individual thing. Why did you select the solvents you tested? Did your data support your hypothesis or disprove? Okay, so then you can talk about, for that first one, that's kind of just your own thing. Why did we select the ones we selected? What was the idea in our head there? Did our data that we collected end up supporting what we picked, or did it surprise us a little bit or disprove our hypothesis? Okay. So hopefully you had a reason for choosing the solvents that you chose. You can talk about that and then talk about whether your hypothesis was supported or not. Okay, so for example, if you picked, I know a couple of groups picked water and hexane because they said, all right, polar, really non-polar, let's just kind of see what happens. Okay, so then you'd really, for the second part, you could say we didn't really necessarily have a hypothesis, or maybe you did. Maybe you thought it would work better in the water, or it would work better in the hexane, and you could talk about whether it did or not. Okay. 2, what explanations can you provide for your separation of the 3 molecules? How is the choice of solvent connected to the separation process? Okay. So what I think you're probably going to see here, okay, this is my guess, and again, this is based on kind of what I thought I was seeing today. I think that you're probably going to see that the water was the best solvent. Okay. I think you're probably going to see that's the one that provided the best separation out of all of them. Probably that's where we're going to get our best RF values from tomorrow. That's my guess. All right. And that would have been my guess initially also for reasons we'll talk about in a minute. The next best, I would have guessed maybe the 2-propanol, and then maybe the ethanol after that. Those both have hydrogen bonding in them, just not as much hydrogen bonding because the water, there are 2 places there where it can hydrogen bond. Okay. So, sorry. Hang on. Well, I'll go ahead and respond to that. That's got to be your hexane. It's got to be. Or else, I don't know. Anyway, I looked at your water earlier and it had moved. So your water probably would be the best, okay? 2-propanol, I'm guessing, would be the next best. Then the ethanol. These might be kind of close, okay, just looking at the structures of them. The acetone, I'm thinking probably wouldn't have worked very well at all, so that's your next. So maybe 1, 2, 3, 4. And then hexane, I mean, we know this because any of you who tested hexane today, it didn't move at all. Okay, nothing moved. So that would be my guess as far as your order. Okay. So then we just need to talk about why. Why did that happen? All right, that's kind of what the question is asking. So water's the most polar out of that list. Okay. And I'm just making that statement. The reason why is because water's, it's fairly small to begin with, and this oxygen is basically pulling on both these hydrogens. So you have a really negative end, or positive end here. Nope, negative. I was right the first time. So you have a really negative end here. You have really positive ends next to the hydrogens, and there's 2 places there where that water can hydrogen bond. Okay. So water is very polar. Now, we also know that water is attracted to ions, right? Ion-dipole interactions. So anytime you've got something that's maybe a little bit ionic, then that's going to actually be very attracted to the water, or the water is going to be very attracted to it as well, okay, however you want to look at it. So these sulfate groups that we've got here, or sulfite groups, I guess, these are SO3s here, okay? These are going to have quite a bit of charge to them, okay? They're going to have strong interactions with the water. So if you notice, all of these have these SO3 groups on them, okay? In addition to a couple of places where they can hydrogen bond. And then this one, you probably wouldn't have noticed. This is a carbon right here, okay? And so you've got what's called a carboxylic acid on this one. And carboxylic acids have strong interactions with water as well. I wouldn't have expected you to know that. Okay. Again, this is fairly complicated organic, so that's why I think it's good if you watch this video. But if you heard me say that just now, you're already watching the video, so you know I can't advertise for people not watching the video, unfortunately. I can in class. Okay, point is, those are the places that are probably going to be very attracted to the water, okay? So what I'm saying to you is these are fairly polar molecules, so they're probably going to be most attracted to the most polar solvent, okay? And you might have sort of taken a guess just by looking at these that was the case, and that the water's going to work the best because you've got polar and polar, right? So really the question here is, well, actually I think this is covered in another question, okay? So I forgot what the question was. Let me look back at it. Separation of the three molecules. Okay. So now we can talk a little bit about our data. And those of you who had water, you might have noticed this. Which one traveled the furthest out of all three?
Water.
Okay, now you guys got, yeah, and which one of your colors traveled the furthest?
Oh.
Blue, okay. So it was red, then yellow, then blue, right? Okay. So what we can kind of deduce from that, just based on the data, and it's good we got at least one group that has those results, is that probably the blue was the most attracted to the water. Does that make sense? Because it traveled the furthest along with the solvent, okay? So blue, we can probably say, is the most attracted to the water out of all of those, okay? Now, that makes sense for a couple of reasons. It's got 3 of the SO3 groups on it, okay? The other thing that's going on with the blue, it's got a place where hydrogen bonding can happen. Let me erase this here. Well, no, I'm sorry, that's a carbon, not a hydrogen. Here, this is a hydrogen, okay? So there's a place here where hydrogen bonding can occur, all right? So you've got hydrogen bonding, you've got these SO3 groups here that are attracted to the water, and then the other thing is this is the biggest out of all the molecules, all right? So biggest equals what? More LDF. It's more polarizable, okay? And if it's more polarizable, then the water could probably be more attracted to it just because of its bigness, okay? So small LDF molecules not really attracted to water, but larger ones would be more attracted to water because they have stronger LDF forces, okay? So the blue, it makes sense the blue is traveling the furthest in the water, okay? The yellow, we've got a couple of the SO3 groups, we've got a hydrogen bonding, and then we've got this carboxylic acid group right here that, again, you might not have necessarily known about that, okay? We've got another couple of places right here where hydrogen bonding can occur. So there's a lot going on in this molecule that would tell us that this one probably can go fairly far as well. Okay, the red went the least far out of all of them, okay? Now the red is comparable in size, maybe a little bit smaller than the yellow. And it only has 2 of the SO3 groups. It's got a place here where it can hydrogen bond. A couple places here. So really, it's comparable to the yellow, but it's a little bit smaller. Okay. So the thing that kind of distinguishes these is the LDF forces. Okay. The blue is obviously it's got more of the SO3 going on here, and then it's bigger. All right. So it's easier to look back on it in retrospect rather than predict it ahead of time. But hopefully it makes sense to you that the blue is going to be the most polar out of all of those. And so it's going to be the most attracted to the water, which means it travels furthest with what's called the mobile phase. Okay? The mobile phase is the solvent traveling up the paper. Okay? The red would have traveled the least far with the mobile phase, which actually helps us to answer another question in just a minute. Okay? What do I need to say about that one? How is the choice of solvent connected to the separation process? Okay. So, because these things are polar, you're going to get better separation if you use a polar solvent, right? That can help to separate them. The hexane, what happened with the hexane, basically, just to use the most extreme case here, this is completely non-polar. There are no OH groups on this. There are no lone pairs of electrons anywhere. I know it doesn't look like it looking at this structure, okay? But this is completely symmetrical, so completely non-polar, all right? What that means is, and actually I did a little bit more digging on this. The filter paper has cellulose in it, which most paper does. But the cellulose actually has a thin layer of water in it, okay? So that's why the water travels up the paper, because it's essentially attracted to the water in the cellulose itself, okay? So what you've got going on, these three, which are polar, are slightly attracted to the cellulose because there's a little bit of water built into the cellulose itself, all right? So you put a solvent like hexane in there that's completely nonpolar, and these things really aren't attracted to the hexane at all, okay? So they just stay where they are. They're attracted to the cellulose, not to the hexane. So the hexane moves up the paper. They don't move with it. You put something like water in there, okay? They're much more attracted to that water that's moving up the paper than they are to the little bit of water that's in the cellulose, and so they move with the mobile phase, okay? And that's why you get movement on the ones that are more polar. Is that making sense? Okay. All right, so that's kind of the idea. So the more polar it is, the more it can essentially pull those dyes off of the cellulose, and they'll move with the solvent, okay? So the 2-propanol, probably the second most polar out of these, okay? And again, the 2-propanol and the ethanol are going to be close. But these two are a little bit polar, but they're not quite as polar as the water, okay? But they both have hydrogen bonding. So those two are probably going to be the next best at moving these things up the paper. But you might not have seen, with these two, you might not have seen a separation of the yellow and the blue. Some of you didn't even see a separation of the yellow and the blue with the water. So you probably would not have seen it there. But you might have seen a red-yellow separation on that one. You definitely would have at least seen the red moving up the paper, okay? With the acetone, I wouldn't expect much separation at all between any of the colors, okay? Because this is less polar. There's no hydrogen here, so there's no hydrogen bonding, okay? And then you've got your hexane, which is completely nonpolar, and we all know that the dye didn't even move at all, okay? So that's kind of the explanation for why these things are happening the way that maybe they did in the lab. Hopefully they did in the lab. Like I said, I was walking around and I was paying more attention to the extremes, the water versus the hexane, and I know those turned out the way that I thought. The ones that are in the middle might be a little bit trickier. So then number 3, what part of the chromatography setup did the molecules interact with, stationary or mobile phase? Okay, and so then you're just going to have to answer that individually for your particular solvents, right? If you use the hexane, in the hexane, the molecules interacted a lot more with the stationary phase, right? They were more attracted to the cellulose in the filter paper than they were to the hexane itself. If you were using water as your solvent, they would be much more attracted to the mobile phase rather than the stationary phase. Okay, here's where it gets a little bit funny. Draw a picture of how the chromatography worked. Explain your picture using the following terms: stationary phase, mobile phase, and intermolecular forces. So drawing a picture of how the chromatography worked. This is fun. And I'm going to cheat a little bit. I'm going to use the pictures they already have drawn on here. Sorry. I know that's not fair. But let's say that we're using water as our solvent. Okay, that's an easy one. So we've got our H2O. Okay, so you've got your negative end down here. You've got your positive end up here. And we have, they're not drawn in, but we have, that's way too big. We have lone pairs on these electrons are enormous. We have lone pairs on all those electrons, okay? And so what's happening here is we're getting a fairly strong attraction of the hydrogens for these oxygens, okay? And you're going to have a lot of water molecules around there surrounding it, okay? So strong attractions are going to happen here, basically anywhere that you've got lone pairs of electrons, right? So on the nitrogen here, you'll have a lone pair of electrons where the hydrogen, wait a second. Is that a lone pair or a hydrogen? See, I can't remember my organic notation there. I don't remember if they just leave the hydrogens off of the nitrogens, or the carbons, I mean, or if they leave them off the nitrogens as well.
You said that,
Yeah, I know. I said earlier I drew a hydrogen there, didn't I?
well, a couple things. So you split that the corners were carbon and then off of those were hydrogen.
Right, for the carbons. But what I can't remember is this nitrogen right here. Is that a lone pair on that nitrogen, or is that a hydrogen? I'm going to stick with this for right now. I think there's a lone pair on the nitrogen. I think, and instead of the hydrogens I was drawing earlier, sorry about that, I think that these are lone pairs on here. I could be wrong about that. But either way, you can draw your pictures for sure on the SO3s, right? You can have and then you can have a water molecule up here. You just need to make sure that the H's are closer to these are really big water molecules too. But there's going to be hydrogen bonding here where the hydrogens are attracted to the lone pairs of electrons on either oxygens or nitrogens, okay? That's going to happen in several different places. And then you've got these OH groups down here where this hydrogen is probably going to be attracted to the oxygen end of a water molecule, okay? Because this has lone pairs on it. It's a horrible drawing. But that's basically what you want to do, is you want to show, and I would do it for water. You could do it for the ethanol or 2-propanol. You could even do it for the acetone, but I think the water is going to be the easiest one to make the drawing for, because then you can show the hydrogen bonds that are forming here between all these different parts. Okay? So that's kind of what they're looking for in the pictures, but they also want an explanation to go with it, because they say that they want you to include intermolecular forces. What were the other two terms that you were supposed to include on that one? Stationary phase and mobile phase, okay? So the mobile phase there would be, and actually, that's the tough part. They want you to draw a picture of the stationary phase. Yeah, I'm okay. I'm okay if you just write stationary phase as opposed to drawing out the molecular structure of the cellulose as well. That seems a bit much to me. But basically, you've got your mobile phase is going to be your water molecules. Okay, your stationary phase is going to be your cellulose, and then you've got your dyes, and then your intermolecular attractions. The main one that we're going to be focusing on here is the hydrogen bonding that's occurring between them. Okay, so however you can do a good pictorial representation of that.
Wait, hydrogen bonding is going between what?
The hydrogen bonding happening between the water molecules and each of the dyes, right? I wouldn't worry about the hydrogen bonding. I mean, you could maybe mention that there's some hydrogen bonding occurring between the dyes and the cellulose, because there's a little bit of water in the cellulose as well, but you don't need to draw that, okay? All right. Evaluate which solvent is the one with the best green chemistry rating. Okay, this is really easy. Should be. What's the most green solvent we used in this lab? The one that I didn't have to tell you to put it in the fume hood. The distilled water, right? Okay, that's the greenest. And it says using the reference in the explanation to strengthen student understanding. They must have a little something there about that, but you don't really even need to look at that. Okay, water's obviously the most green solvent we used in this one. What intermolecular forces does this solvent form with the 3 molecules in the mixture? Which one? What's the main intermolecular force? Yeah, I mean, we've already talked about it several times, right? Which molecule spent the most time in the stationary phase? Now we can kind of zip through these because we've talked about all the conceptual stuff. So based on our data, which one spent the most time in the stationary phase? which dye? Red, yellow, or blue? Red, right? Okay. Because the red traveled the least distance on the paper. Okay. And again, the question is why? Can we answer that based on what we talked about before, about the polarity of all of the three molecules? Okay. Yeah, it was just basically the least polar out of all of those overall. Okay. And for the reasons we talked about, one, it's and probably the major one is that it's basically the smallest out of the molecules. So it has less LDF. It's less polarizable. Okay. And then you could maybe also mention that the blue has the three sulfite groups coming off of it, and the red only has two. But yeah, the red and the yellow are going to be close, but the red's a little bit smaller, so that's probably the tiebreaker there. And then 7, calculate the RF values for each chromatography trial you completed and include them in the data table. I don't know why they don't have you do that before you answer all these questions. That doesn't make a lot of sense to me. So basically, number 7, you're already going to have that answered in your claims and evidence section. So you can just forget about that one. As long as you put it in claims and evidence, you don't need to worry about re-answering it here. Okay? And then argumentation and documentation, write an explanation of how intermolecular forces and molecular structure determine the ideal solvent for use in the separation. Cite specific evidence from this experiment. So I guess there, just give me a little summary paragraph at the end. And again, this can still be in your how did my ideas change section. But just a little paragraph here that kind of summarizes, here's what was going on in this lab with the intermolecular forces. Okay? Again, I know we jumped from really simple molecules to really complicated stuff with this lab. That's why I'm trying to give you a little bit more support on this, because the one thing I do like about this lab is it lets us get into a little bit of organic chemistry, which we did not have the opportunity to do, unfortunately, with this particular unit. So, all right, that's it. And as long as you write it up that way, you should be good on this lab.